So we are going to talk about polynomial functions and their zeros today. Zeros, typically we sort of think of zeros as your x-intercepts. And it is true that our real zeros are x-intercepts. But the definition for a zero is going to be given a polynomial function p of x. If p of a equals 0, then a is a 0 or root of p of x. So we see here that the word 0 and root can be used interchangeably. You might see either one of those. If a is a real number, then x equals a is a 0 of p, and then x minus a is a linear factor of p. So if we have real roots, right, if a is a real number, it's an x-intercept on your graph. And then if we have an x-intercept on that graph, then x equals a is a 0, which means x minus a is a linear factor, right? So we need to keep those two things in mind. The opposite signs that we see there are going to happen in our equations. So if you have a linear factor, x minus a, it's repeated n times. The corresponding 0 of the polynomial will have a multiplicity of n. I've opened the wrong one because I've opened the one that's already filled in. Hold on. I want the one that's not filled in. Let me back up. I want this one. Okay, so you should have talked about some multiplicity in Math 3 whenever you're talking about zeros. So typically, we know that the graph of a polynomial passes through the zeros on the graph. However, when a 0 has a multiplicity greater than 1, the graph will behave differently near the 0. So passes through the zeros on the graph is what we're looking for. So if we look at this function that they have graphed for us, y equals negative 0.01 x plus 4 times x plus 1 times x minus 3. And then the x plus 1 is cubed, the x minus 3 is squared. That is graphed to the right. Notice the behavior around the zeros of the function. So first of all, let's just notice the zeros, right? Zeros are things that are going to make this a function equal to 0. And notice if we've got a factor right here of x plus 4, let's look at x equals negative 4, right? The factor is what we see in the equation. The 0 is going to have the opposite sign. So at x equals negative 4, I have a 0 on the graph, which is what we would expect to happen, right? Now, notice here, that line just passes straight through, right? At x plus 1, that means I would have a 0 at x equals negative 1. So, yep, I've got a 0 right there at x equals negative 1. Now, I still have a 0 that passes through, but it's got a little bit of a squiggle there, right? I see like a concavity change. This is also a point of inflection for this graph right here. So, while the graph does cross, I do have a little bit of a curve there. This is what you're going to expect for odd multiplicities greater than 1. And then the one that's going to be one of the most important things for us to see is right here, x equals 3. All right, at x equals 3, notice x minus 3 is raised to the second power. Do I cross the x-axis here? I do not. I just see the graph sort of bounce off of the x-axis. Now, bounce is not a mathematical term, right? But it's a really good way to describe it. What we would say there in mathematical terms is that the graph is tangent to the x-axis at x equals 3, right? So tangent, remember, means just touching at one point. So this is tangent to the x-axis. Now you might be like, oh, but the x-axis crosses this graph more than once. Your tangent line can be tangent just locally in that area. Like if we cut off part of this graph, then that would be a tangent line. It's okay if it crosses over here later at these crazy places. So the multiplicity of a 0 is the exponent of its factor. So x equals -4 has a multiplicity of just 1 because there is no exponent here, so we just have that term one time. X equals -3 has a multiplicity of 3, and I'm sorry, x equals -1 has a multiplicity of 3, and x equals 3 has a multiplicity of 2. Okay, so you can see here the correct terminology. The graph of the polynomial is tangent to the x-axis at x equals 3. And here you may want to highlight or underline this. The graph of a polynomial will always be tangent to the x-axis at any 0 with even, oh gosh, I thought I had the highlighter, even multiplicity. All right, and that tangent to the x-axis means bounces off the x-axis. Okay, so our first examples ask us to find the degree of the polynomial, find all real zeros, and state the multiplicity for each 0. So depending on how far they have factored this is going to depend on how easy the problem is to do. So A is factored completely. You cannot factor that any further, right? Everything's broken down into linear terms. B and C are not factored completely, so you're going to have to factor a little bit further for that. So normally we think of the degree as the highest exponent. That is true if our polynomial is in standard form, if it's multiplied all the way out. If the degree is factored, we need to think about each 0 and what the multiplicity is for each one, and then sort of add that together. Okay? Or you can think about multiplying it back together. What would your highest exponent be? For this, I see x plus 1. That tells me that I have x equals -1 as a 0. But I don't have any exponents with that, so that one has a multiplicity of just 1. Sometimes they won't list it if the multiplicity is just 1, because that's the standard there. Here I see x minus 4. That gives me a 0 at x equals +4. This factor has an exponent of 2, so I have a multiplicity of 2 here. There is another 0. It's not quite as obvious, though. What is the other 0 on this one? Does anybody know? It's going to be 0. It comes from this term right here, right? Because essentially what you're supposed to be doing is set each term equal to 0. Like when you do x plus 1, what you're really doing is x plus 1 equals 0, and then you're subtracting the 1 from both sides, and you get -1. All right. So what we're doing here is -2x to the third equals 0. Well, you could divide by -2. You got x to the third still equals 0. And then you can cube root both sides. The cube root of 0 is 0. Right? So if you have an x that is factored out like that, that's going to give you 0 as a 0 for that function. And then the multiplicity of that is the exponent that goes with it, so we have a multiplicity of 3. So I've got 3 zeros, so I have what we would call 3 distinct zeros here. But x equals 4 has a multiplicity of 2. X equals 0 has a multiplicity of 3. So I actually have a degree of 6 here. There are 6 zeros of this function. It's just some of them are repeated there. Because this one counts once, This one counts twice, so there's your 3. And then this one counts 3 times, so that gets you up to 6. Okay, I said B and C are harder because they're not factored all the way. So you were like hoping and praying that factoring would just be gone, and it just never goes away. It's always one of the ones we kind of struggle with in Math 1, and then usually by Math 2, like my top students have kind of got it mastered. Although you start throwing a number in front of your x squared, they still have a little bit of trouble. Which piece will factor here? X squared minus 4. Because x minus 2 is already linear, can't get any more simple than that. So the 3 we're going to hold on to. How can I factor x squared minus 4? X plus 2, x minus 2. It's a difference of squares. It's one of those special ones where the middle terms go away. And then I've got x minus 2 to the 4th power. Now, do you guys see anything special that has happened here? Yes, I can write it as 3x plus 2, x minus 2 to the 5th power. I can put those x minus 2's together right there. And so now I can talk about the zeros. I have x plus 2. That is going to be x equals negative 2 with a multiplicity of 1. And I'm going to have x equals positive 2 with a multiplicity of 5. Do I have any more zeros here? We've got like a greatest common factor factored out here, a lot like we had over here, but does it have a variable? No. So can it, like if we set each piece equal to 0, can 3 equal 0? No. So you're not going to get a 0 out of that. If you have a greatest common factor that's just a number, there's no 0 that comes from that. What that's doing is it's like stretching the graph up and making it taller, or squishing the graph in and making it shorter, but it's not actually giving you a 0 from that point there. So if I have this 0 only counts 1 time, but this 0 counts 5 times, then my degree here would be 6. Okay, C has several things that will factor. If I look at x to the 3rd minus x squared minus 6x, I'm going to have to factor a couple ways for this. What's the first thing I should do to factor that? You're going to do a GCF. It has a greatest common factor because every term has an x. So you can factor an x out like this, and it'll be x squared minus x minus 6. And I'm just going to leave the second one alone for right now. Okay, so now I have both of those here will factor. Let's see. Most of you guys had Miss Ball for Math 1. Is that correct? I know a few of you had me, and you might have anybody else. Miss Martin, a couple Miss Martins. So, I know Miss Martin does X method whenever she teaches factoring. Miss Ball, I don't know because I know Miss Ball's done it a lot of different ways. Yeah. So, I generally, like, X method is fine. It's just a trick, really. I just really want you to be able to, like, factor and look at it. If you're doing X method, what you're thinking of is you're multiplying to get the last number, -6, right? You're adding to get the middle number, which would be -1, right here. It'd be really good if you're just, like, doing it in your head at this point, where you don't have to, like, write the X's out, but, you know, if you need it, go ahead. I'd rather you be right there. So we're looking for numbers that multiply to give us -6, but add to give us -1. Okay? -3, +2, right? Multiply to give us -6, add together to give us -1. So we'll have x minus 3, x plus 2. That's how we'll factor that first one. Then over here, we want to multiply to get a positive 12, but add to get a negative 7. Okay, negative 4, negative 3, right there. Negative 4 times negative 3 gives us 12. Negative 4 plus negative 3 gives us negative 7. Is that coming back? I know some of you had Math 3 last semester, and we're doing this. Some of you have not seen math in over a year and might be a little bit rusty. But hopefully it'll come back quickly. So we got x minus 4, x minus 3. And then we want to combine the ones that go together. So we'll get y equals x times x minus 3 squared, x plus 2, x minus 4. And so that x that's just out there by itself, what's the 0 that goes with it? 0. Right? If you have an x that's factored out front, that's just a 0. It has a multiplicity of 1. For the sake of space, I am not going to write multiplicities if they're 1 here. I've got x equals 3. That one has a multiplicity of 2. I've got x equals negative 2. And I've got x equals 4. So I've got 4 distinct zeros, but one of them counts twice. So my degree here is 5 for that one. Okay, so this is all for real roots. But sometimes we have roots that are not real, which sounds insane, right? It's like, why did somebody come up with this? You know, whenever, I can't remember which mathematician, I read about this recently actually. Can't remember which mathematician it was that decided we were going to call the square root of negative 1 an imaginary number. But whoever it was, I want to go to them and be like, let's come up with a better name for this. Because the word imaginary, like whenever he should have pictured teachers having to teach this to children later that hate math. And the moment you tell them that they are going to be doing imaginary numbers, they're like, that's ridiculous. Why are we learning about imaginary things? But imaginary numbers are just a way of dealing with the square root of negative 1. So I read an article that I mostly understood but did not entirely understand the other day about how, like, quantum theory is reliant upon imaginary numbers. Like, no, don't ask me how, because I do not know anything much at all about the quantum theory stuff. But it was like the quantum theory uses a lot of negative numbers as an easier way to solve it, but there's also a real way that you can do it. But this article was saying that they have discovered that there is a certain part of quantum theory that has to be done with imaginary numbers. So either way, if you get to the point where you're working on quantum theory, I didn't quite make it that far in school, then imaginary numbers become very essential. Some of you, like, still dumb, not ever going to do quantum theory, but I do kind of like to know a little bit about things that are out there, even if I'm not the one doing it. I won't be creating a quantum computer anytime soon in my future, but I like to know a little bit, like maybe about what's going on. So I find it kind of cool. I had a whole class on this. They tell me that you need imaginary numbers for things like cell phone networks and all kinds of crazy stuff. I took a whole class on complex numbers in college, and honestly, we never got to the point where we were using it for anything. So I'm pretty sure if you ever find yourself using complex numbers in your day-to-day life, that you are somewhere doing some crazy stuff that is well beyond what we're getting to here. You're going to need it as some building blocks, but it's pretty crazy stuff. So complex roots are ways of talking about roots that you will not see on the graph. This means you will not see them on the graph. Could graph them on the complex plane, which we saw with our modulus question, but again, not what we have to do here. So, for example, the graph of f of x equals x squared plus 1. That's just a quadratic that's been moved up 1. Well, when you move that quadratic up 1, it doesn't touch the x-axis anymore, right? So, if we want to find the zeros of x squared plus 1, we can take that function and set that function equal to 0. And he goes through the steps over here, but I'm going to write them down to see the process. Well, if we want to solve this, this is not a hard equation to solve, but you just run into a problem, right? So I could subtract 1, beautiful, lovely, x squared equals negative 1. And then I could square root both sides, right, to get rid of that square. And so x equals plus or minus the square root of negative 1. Whenever we, remember that when we square root both sides of an equation, we need to put that plus or minus there because we could have a positive or negative value that would work for that. But what is the square root of negative 1? It's not a real number, right? Because there's nothing you can no real number that you can multiply by itself to get negative 1. In fact, any square root of a negative number is not going to be a real number. Because if you multiply a negative times a negative, you get a positive, right? It's impossible to multiply a real number by itself and get a negative number. So, mathematicians, I wish I could remember the one that's credited with this. I'll have to go look that up. But mathematicians kept running into the square root of negative numbers. Like, it kept happening, and they needed to be able to deal with it to get further in what they were doing. So they said, how about we just call this one I, right? So this is going to be x equals plus or minus I. And so since they call that I, that allows them to deal with these types of numbers and analyze the situation further, right? For all the quantum theory and whatever else that they're going to do with it that we don't quite get to that point in this class, right? So these are called complex zeros. They do not show up on the graph. They are not x-intercepts. But if I plug I back in, right, if I do f of I, that would be I squared plus 1, which would be the square root of negative 1 squared plus 1. What happens when you square a square root? Those cancel each other out. Now I've got negative 1 plus 1, and it does in fact give me 0 whenever I plug in I, right? So this is a 0, but it's not an x-intercept. Okay, and those are called complex numbers. And complex numbers complex or imaginary roots always come in pairs. It comes from the fact that, like, when you're square rooting both sides of that equation, you get a plus or minus, which is going to give you two different roots. So a very key understanding here, all imaginary roots come in pairs. In fact, they are called the conjugate pairs. And the conjugate pair is what you get if you just change the sign in the middle. So if a plus bi is a root of f of x, then so is a minus bi. Okay? So, just looking at these right here, I actually think C and D are a little bit easier to do. Here, if you're looking for the conjugate pair for these numbers, all you do is change the middle sign. So, like here, if I've got 2 minus 3i as a 0, then 2 plus 3i would be a 0. And if I have negative 4 plus 2i, I would have negative 4 minus 2i as a 0. You only change the middle sign, not all of these signs. Okay? A and B don't have a first number, right? That just means that number is 0, right? So if I've got positive 4i, then negative 4i is the 0 that goes with it. Or you can think of 0 minus 4i, 0 plus 4i, and 0 minus 4i. And then if I have negative I, then positive I is my conjugate that goes with it. So fundamental theorem of algebra obviously is like a big deal, right? Because they named it the fundamental theorem of algebra. You do this in Math 3. So the fundamental theorem of algebra just tells you that a polynomial of degree n has exactly n complex zeros when counting multiplicities. So if you have a polynomial with a degree of 7, then you have 7 complex zeros. Now, this word complex right here does not mean that the values have to be imaginary. This could be real or imaginary. So you can just think of it as all total zeros. So let's look at some of the types of problems you'll see for the fundamental theorem of algebra, right? For example, 3. The graph of the polynomial function f is shown in the figure above. It is known that x equals I square root of 3 is a 0 of f. If f has degree n, what is the least possible value of n? Okay, so they gave me a complex 0, right? So I know x equals I square root of 3 is a 0. That also means x equals negative I square root of 3 has to be a 0 as well, because complex zeros always come in conjugate pairs. So even though they didn't mention it, I have I have two imaginary zeros. Okay. Then I want to look at the graph. Okay. And on the graph, I have 2 zeros. I've got x equals negative 1 and x equals 3. Now they are asking me for the least possible degree. So I only from the graph can tell that here at x equals 3 that I have an odd multiplicity, and I can tell here that I have an even multiplicity because the graph is tangent to the x-axis. It just goes up and bounces off of the x-axis. So I know for sure that I have an odd multiplicity here, and I know for sure that I have an even multiplicity here. Now, you cannot answer the question how many complex zeros does this function have? But you could say, what is the least possible degree? Right? It is possible that the degree is higher. But the lowest odd number that we know is 1. So I'm going to say if we're looking for the least possible value of n, that the multiplicity of the graph at x equals negative, I'm sorry, I put that in the wrong spot. At x equals 3 is 1. So multiplicity of 1. They're not going to ask you for what's the highest possible value degree because that'd be infinite, right? And then at negative 1, I know I have to have an even multiplicity here. So the lowest even number I can use is a multiplicity of 2. So I have 4 distinct zeros, but I've got this one right here that counts twice. So the least possible value of n is 5. Okay, does that make sense? I've got 2 that I can see, but this one counts twice, so there's 3 real zeros. Then I have to have 2 imaginary zeros, giving me 5 total. Okay, so when we're looking at inequalities here, when we write f of x, we are referring to the y, so it looks better, y value on the graph of f. So if the question says that f of x is greater than 0, that means the graph of f is above the x-axis. They also might say f of x is positive, right? And then if f of x is less than 0, that means the y coordinates are below 0, so f of x is below the x-axis. Here. So they might ask you where f of x equals 0. You're just given the x-intercepts for that graph. So for this one, you would get x equals -3, x equals -1, and x equals +3. If they ask us for the parts where f of x is greater than 0, we are looking for where the graph is above the x-axis. So for this graph, I'm going to assume, since they did not put dots at the end, that they meant that there are arrows here. If you see a graph that I've done on the test and it goes all the way out to the end and there's not dots, assume it's an arrow, because Desmos won't let me put arrows on the end, and I use most of my graphs from Desmos. So my intervals here, where this happens, are going to be -3 to -1, right? You're given the x coordinates where this function is above the x-axis, and then also from 3 to infinity. If we are looking at where this graph is below the x-axis, we are looking at this part of the graph and this part of the graph. And so that is going to be the x-coordinates over here are -infinity. I'm not thinking about the y-coordinates. It has nothing to do with it going down. But it's -infinity over here up to -3. I want to use a bracket right here because I have an or equal to sign with the 0. So I can equal 0. I used parentheses over here because I had a greater than sign, meaning that my function could not equal 0. So I want to use a bracket here. I did not use a bracket with -infinity because you should never use a bracket with infinities. You can't actually get to infinity. And then I've got also from -1 to 3. Okay, questions there? That's similar to our increasing, decreasing, concave up, concave down sort of stuff. You're reporting that the domain with the x values. All right. Oh gosh, we don't have time. Don't have time. Okay, let's get down to this. We're going to do this because we do have time to do this very quickly. So, determining the degree of a polynomial. This is very similar to what we were doing with our tables with our linear and quadratic. In fact, it is what we were doing. All right, so the first thing you want to do is check to make sure that your x's are increasing at a constant rate. If they are not, you are not going to be able to check. So I can see that for this table, my x's are increasing at a constant rate. Then you want to look at the first difference, the second difference, the third difference, and so on for this graph. So from -2 to -3, that goes down 1. From -3 to -1, that goes up 2. From -1 to 4, that goes up 5. And from 4 to 12, that is up 8. Right there. So first difference, this is not a first degree function because I'm not getting all the same answers here. It's not linear, right? Linear would be first degree. So then we'll do this again. From -1 to 2, that goes up 3. From -2 to 5, that goes up 3. And from 5 to 8, that goes up 3. This is quadratic, which is a second degree. So our degree equals 2. Okay? But if I look at B here, I can see my x values are increasing at a constant rate, so I can check. So if I go from -2 to 0, that is up 2. And then from 0 to 10, that is up 10. And then from 10 to 27, that is up 17. And then from 27 to 50, that is up 23, I believe. Is that right? Okay. Then I want to do second difference, so I do this again. Here we have up 8, up 7, and up 6. So this function is not quadratic, right? Because I'm not getting all the same numbers. But if I do it one more time, down 1, down 1, this one is a degree of 3 because my third difference was constant. And it would be the same, like if you go out to the fourth difference being constant, then you would see a fourth degree, and fifth would give you that. So we're definitely going to have to skip part of what I was going to give you for homework. So let me pass these out and I'll look through and tell you which ones we're skipping. Good news is, since we're behind as always, all of my life, in all aspects. But the good news is I was wanting to try to squeeze in the test this week. I'm not going to try to do it. We were already too short. So my plan right now is for us to do 5 today, 6 tomorrow, take a quiz on Thursday. But we got a little bit of room where I can push it to Friday if I need to. So we'll just see how far we get. So, oh, I gave you the notes. No. Okay, you're going to give me that on the way back out. We're passing them all back up to the front. Gosh. I was wondering why I ran out of them. I thought I made another copy. Oh. Better get it together today. Let's see. We can do the whole front page. We're good there. We can do the tables. Okay. 1 through 18. Do 1 through 18 for me. I think you should be able to do those. And then we will finish this up tomorrow and just see where we get with it. We may push 1-6 to back there. Yeah, make sure. Oh, you still didn't get the There you go. Thank you. All right. Take these back. I'm pretty sure teachers do not have the authority to let you get your card. Did you get the homework? If I ever pass you out the wrong thing on accident, it's always posted on Canvas and you can go look there for the actual and just write it on paper, but hopefully everybody got the assignment by then.